Okay, everybody, what we want to try to do today is talk about double bonds and triple bonds and see how the anatomy of those bonds actually work as opposed to singles. And it's just a quick little explanation on this, and let's get to it. So we talk about sigma and pi bonding, and we got to be able to tell the difference between how a single bond forms versus how a pi bond forms, or a double bond or triple bond. So it's just really a matter of orientation of the electron cloud and how that actually overlaps. And it's the angle of the overlap really that really makes the difference, and hence brings everything into power here. So if we take a look quickly at get my pen the right way here. Good job. All right. We think about a sigma. We'll take a sigma bond first, and really, a sigma bond is simply a head-to-head overlap of the bonding orbitals. So when I say head-to-head, that simply means that the one overlap of the bond, like this. Okay, if that's the bonding electron cloud with one dot on a carbon, is going to take the other overlap, and that's going to overlap the other carbon like that, where they're going to point at each other in that angle, and that will end up producing a covalent bond. Okay, and that creates a single, very strong covalent bond, and it's sometimes referred to as a handshake bond. If you reach out your hand and you shake someone's hand, and you have a nice tight grip, that would produce this head-to-head orientation of your hands. One hand would point towards the hand, other one would point towards the other hand. You'd handshake. Okay, some things you need to keep in mind is that a sigma bonds must be formed before you form a double or a triple. Okay, so you're always going to lock in that bond first, and then if you have extra bonding, the extra bonding would be your pi bond or your double or triple. All right. So if you wanted to count how many single bonds in ethane in this case, okay, if you look at my pictures here, um, we'll take a look at you know you count this bond, this bond, this bond. So you'd have all your bonds here. You'd have one, two, three, four, five, six, seven. So I guess one, two, three, four, five. So you'd have seven sigma bonds. So single being sigma bonds. All right. So if you take a look at this, you'll see the sigma bond here, and again, sigma is this little Greek letter here. You'll see how the electron cloud face towards each other. Again, same thing here. This electron cloud faces the electron cloud in the hydrogens. So when you look at this molecule C in ethane, okay, you'll see each of the bonds is a sigma bond, so they're all singles. All right, in pi bonding, things look a little different in pi bonding. All right, so if I go backwards a little bit, okay, so a pi bonding is a weaker secondary side-to-side bonding. So instead of sigma being head-to-head, is now side-to-side overlap of orbitals. That happens a little bit differently. You must form your sigmas first. Okay, pi bonds, because they are weaker, they will be broken before you break the sigma. So if you have a double bond that has a sigma and a pi, you're going to break that pi bond first. Okay, now interesting enough about a pi bond is they can move freely through the pi bond. And I'm gonna go through this with you in a minute right now. Okay, and we use the term delocalized. When something's free to move around, it's actually delocalized. Okay, and because of that, if you have delocalized electrons and they can move, you then can conduct electricity. So that's going to be an interesting part of this. So if you take a look at the rest of the pictures here, I want to be able to draw this for you. And I know sometimes the picture doesn't really do as much justice, but if you have a situation where you have something like this, where you have a double bond between two carbons, I want to make sure you can see the way this is. And again, you don't have to be able to draw this. You really just have to know what it is. So in this case, let's just say I have carbon, and then I have a carbon, and I have my sigma bond here, and I have my sigma bond here. So I have my pair of electrons in the middle. Okay, and we know that if carbon is going to be bonded to other hydrogens, those would also be sigma bonds. All right. Now, the important thing is to realize, so that would represent this picture here. So here would be your single bond, here would be your single bond, here would be a single bond and a single bond, and then a single bond in the middle. So that would match this picture here. Okay, so there's your sigma bond. Now, what a pi bond does is based on this geometry. What a pi bond does, it has an upper area and a lower area where the extra dot would be, right? So each carbon has a dot that hasn't bonded yet, right? We have the extra bond we need to form. So I just want you to think that this dot here is actually in both of these cloud, both of this cloud. Okay, it's actually in both. So the electron cloud is both of these. Okay, and if you notice in the sigma bond, they're pointing at each other, like the clouds are pointing, but these clouds are actually parallel to each other. So that this is on one side and that's on the other side. So what happens is that these clouds will actually bend over and connect. So we're going to connect these clouds together, and they're going to have a side-to-side overlap. So they're gonna overlap this way, and this is going to overlap with this guy, and they're going to be like this big one-shaped cloud as they all combine into this above layer and lower layer. So think of that as one half of a bond, and this is the other half of the pi bond. So the pi bond is actually this whole entire thing, and that's what would make the double bond. So the double bond is actually when you combine the upper and lower version of a side-to-side overlap. This bends to that. Now, electrons can actually move around this pi bond. They're allowed to go in this electron cloud, both electrons. Now, how we actually organize that and how we draw that is drawing a double bond. Okay, we draw it as a double. Okay, I know it looks like triple, but it's not a triple. This is a double. A triple bond would be the same thing here, but you'd have one going out at you and into the board. So into the screen and out of the screen would be the triple bond. All right, so really, what are we trying to do here? Basically, you form a sigma first, and then you draw a pi bond if you need extra bonding between two elements. And if you need a third bond, then you draw another pi bond. All right, so in summary, a single bond would be 1 sigma, and this is really all you need to know. Okay, a double bond is 1 sigma and 1 pi. So I like to think of the sigma bond as being the dinner, and you have pi for dessert. Get it? Get the joke? Pi for dessert? Okay. So pi is like extra bonding. It's the extra bonding that you need, all right, to make the octet or whatever you need. All right, so, and again, a triple bond would be 1 sigma, okay, and 2 pi bonds, all right, for 3 total. So really the summary is really what you got to know. Do you have to draw this? No. Okay. I would know this part, okay, because it's important to know what the properties are. And what the properties are of sigma and pi bonding, because it's going to be important to know for later, because certain elements can do this. Okay, and just understand that it also, as you go in this direction, okay, the bonds get stronger, and shorter. Okay, I know I'm squeezing this in here, but the bonds get stronger and shorter as you move this direction. So one sigma bond is actually longer than the triple. Both atoms get pulled in closer, and it's also tougher to break all 3 bonds than it is to break 2 or break 1. All right, so that's really the angle. If you want to take a look at this, just some pictures here. Okay, again, in your packet you'll see this is the molecule benzene. Okay, and benzene has benzene is an interesting one because benzene has pi bonds over a large area. If you look at this benzene molecule, benzene is actually a hexagon of carbons like this. It looks like this: carbon, 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 and a carbon here. Okay, and it looks like that, and it's got alternating double bonds, and it's got a hydrogen, 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 like spokes of a wheel. All right, and around the middle here, this pi bond can actually rotate around the middle here. So this actually extends around the whole area of the inside of the molecule. So when you look at this, you'll see these all green guys will join at the top, and the blue guys at the bottom will join at the bottom. So that's what your pi bond is. So if you take them and join them, they look like this, and you'll see electrons are going to be allowed to run around inside this tube. These are all electrons that can move about the surface and move about the surface. So, this makes for electrical conductivity when you start connecting molecules together. If you connect all these hexagons together like that, and you'll see there's multiple hexagons connected to multiple hexagons, you can have electrons can move throughout this entire sample. Okay, and that makes for very important carbon bonds here called carbon nanotubes that can actually bond, all right, and with each other. Okay, and not only that, you can have electrons that run through this entire network here. Okay, and that makes for an interesting thing. Okay, on this side, you'll see that another more different hexagons can be put together in a different way. So there's different ways you can bond these together. The key is that when you have these extensive pi bonding. But again, the previous slide, you really just want to know the summary here. That's the important part at the bottom. Okay, and be able to tell the difference between a sigma bond, which is a head-to-head overlap, which is a stronger single bond, and a pi bond, which is extra side-to-side bonding. All right, no big deal. Okay, we'll talk to you soon.